Alright, once again we're having physics class. Going over Hexagontum physics, Shaughnessy's law of gravity. And I'll put the equation up later, but basically I want to give you an idea of what is going on with mass above the ellipsoid. This would be the Earth right here, and we'll play with pyramids or mountains. We call them mountains, geometrical mass above the ellipsoid, and basically we'll put a mass here and basically a mass at the same latitude. That'd be a latitude line right here, about the same. It's approximately the same latitude. So you got mass A, mass B. And there's a gravitational connection between these two. Now, if you went over and artificially removed mass A from the equation, basically mass B would is lowering the gravitational force of mass A. So it's pulling this direction towards mass B. It's pulling towards that way, and what it does, it's lowering the gravitational field of A. So what that in turn does, it allows mass to reform at location A, be it a mountain, volcano, and that's the two natural things anyways, mountains and volcanoes. So that's what's going on. Now as this thing grows, the reverse gravitational fields will then start to change direction, and you'll have it go, it'll be pulling up towards mass A when it comes up out of the crust of the Earth or the surface of the Earth. So when they're balanced, you have mass B pulling from the gravity neutral zone, the GN, and that's in the core of the planet, and you have a balance between the two structures. So that's what's going on there. Now, same thing is going on, say like every large pyramid structure on the planet has a volcano 180 degrees opposed from it. So if you look, I want to make sure I stay in frame. Let me just wipe this off. So if you look at if you're looking at the top of the Earth like this, and these are rings of latitude, okay, as the axis, you can have a mountain range here, and 180 degrees you'll have a mountain range there. Same with the pyramid. Put large pyramid clusters here, 180 degrees away you'll have a volcano here. So pyramid, volcano. Alright, that's a fact. You go get a globe, check them out. Giza lines up with the Hawaiian hotspot. All the Nile Valley pyramids line up with the Hawaiian hotspot. Pyramid of the Sun, which is like just a small percentage of the hundreds of pyramids that are actually located down there in the Yucatan Peninsula, Mexico, Central America. They all line up with Sri Lanka and a few islands on the Sumatra subduction zone. The other big alignment is the Shen pyramids. We got the Shen pyramids in China line up with Bermuda. Okay, Bermuda. These are two extinct super calderas that make up that island actually. So they're 180 degrees away from each other and on the same approximate latitude. I might as well put in Pyramid of the Sun. That's Giza. Pyramid of the Sun. And then you have Sri Lanka and a few other islands in the Sri Lanka. you have a few other islands in the Indian Ocean. Anyways, that's what's going on. You got these alignments, they're crossing each other. This goes on, you know, as many pyramids you can find, large pyramid structures. You can tie them into volcanic islands or volcanoes anywhere in the on the planet. It's the southern and northern hemisphere. You also have mountain ranges that line up with mountain ranges. The Himalayas line up with 3 mountain ranges in the United States, North America. The Sierra Nevadas, the Rocky Mountains, and the Appalachian Mountains that I'm actually standing on right now, or part of it anyways. So with that in mind, that's kind of what's going on with gravitational effects on the planet. So we did the mass A, mass B, how it pulls on each other. That balances the planet out. So, you know, Pangea, they thought, like, you know, they had the planet here, and they had like all the land mass on one side, and then it split apart. Absolutely ridiculous. If that ever happened, the planet would rip itself apart if you had all the land mass, you know, on the side. The reason everything in the universe is like round and, you know, kind of like got a spherical shape to it is because gravity's force on it. And you have a large mass on one side, it's going to lower the gravitational field on the other, and it's going to allow that to grow to balance it out, you know. Otherwise, things would never click together. They would just, you know, spin up and just disintegrate. Okay? All right, so that's hexagonum physics. I had to leave quantum mechanics, quantum physics, relativity, and anybody that else had had some kind of published theories on how things work on the planet. Had to create my own discipline of physics called hexagonum physics. I just got trapped. You know, I got tired of arguing with you people. I couldn't take it anymore. All right, here's another explanation of what's going on that you see every day that's also been misrepresented by the mainstream. All right, here's the Earth, the green Earth. All right, and we'll have the ocean. This is the ocean at high tide. Okay, that's a lousy picture, but it's probably more closer to know. All right, we get the moon over here. All right, you got the moon high tide. High moon. Okay, yeah, that's good. High tide. Then you have the moonless high tide, which the mainstream physicists tell us that it's the centripetal forces that are spinning the water off of the planet because it's rotating. Absolute ludicrous nonsense. Don't even commit any of that crap to memory. If you're paying for it, I'm sorry they told you it. I taught it to you. This is the moonless high tide. My patience is at an end, so if I'm a little cynical with the mainstream, you'll forgive me. I've got reasons to be this way. Plenty of reasons. But anyways, this is the moonless high tide. No moon, but yet the tide is high on this side of the planet. Like I said, they tell us it's because of the planet spinning, and it's forcing the water, you know, off to the side. It's absolutely lunacy. The reason you got a high tide on the moonless side, it's not as big. It's smaller. Smaller on this side, and this is obviously larger. This is the larger side. Oh, got the iron there. All right. The reason is just what I went over. Mass A or mass B is bigger than mass A, and it flexes the gravity neutral zone down in here. The GN, gravity neutral zone, actually changes shape. It changes its shape. But it also, it's pulling here, and what it does, so you have a higher gravitational field on this side of the planet, and it lowers the gravitational field on the moonless side. Gravitational field on this side. So what it does, when it lowers the gravitational field, this water actually rises. You're actually flexing the gravitational field on the other side of the planet, opposite of the moon. That happens twice a day. You get 2 high tides and two releases, 2 pulls, as I call it. And that's basically what's happening on your planet. You know, it's It's just the way it is. It's not that this has nothing to do with centripetal effects, centrifugal force, or anything. It's just forget about it, erase it from your mind. It's being lowered by this force right here. This is pulling the gravity neutral zone out of its equilibrium when the moon's on that side, and it's lowering the gravitational field on this side, and it's allowing the ocean to rise opposite side of the planet. All right, so the formula that expresses all this is AMC squared divided by dB equals S. dB, you gotta do small letters, big letters, sorry about that. dB, what is wrong with this pen? Equals S. Alright, A is the angle of mass off the planet. Okay, and that's the angle in radii. Okay, M is the mass. So if you have the angle of this coming off of the above the ellipsoid, this is the ellipsoid right here, this is the planet, the actual surface of the planet. You measure that in radii. Okay, mass of the ocean that's being pulled off, or mass of a pyramid, mass of a mountain, mass of a volcano, mass of a hill. Okay, this works for water and solid things. You know, in the world of gravity, everything's translucent anyways, but that's just to give you something to connect to. And this is speed of light squared. Okay, that's the theoretical speed of gravity, graviton as it's flowing through through mass. D is distance, so it'd be you want to measure the distance, which is generally 4,000 miles to the center of the Earth. It's like 4,000 miles on average, you know, somewhere there. I just had to give it a number. I mean, I got to balance the formula. I don't even want to put this stuff on here, but you know, after arguing with mathematicians for 3 years, I said, okay, you can have your distance. All right, dude, calm down. All right, okay. So I give him the distance, and B is the gravitational constant. What the gravitational constant of the Earth is at this particular level, you write that in, and then it equals S. S is units of Shaughnessy. I said, well, if I got to come up with all this stuff, I might as well have my own units of measurement, right? Everybody else did, you know, Newton, Einstein, a few other people running around. So anyhow, that's what I got. That's it. So I think I explained it pretty well. What are we up for a time here? I like to keep these pretty short because it does get boring. All right, I think that's about it.